This lecture is going to be on the theory of congruences and modular arithmetic. I'll go through some of the history, how we can use it, some axioms, and some real-life examples of modular arithmetic. So, starting with some of the history, modular arithmetic was first proposed by Gauss in 1801. He published a book called, I'm not going to try to pronounce it, but I think it's Disquisitions Arithmetica. And this was actually very useful because before that, mathematicians used to use remainders quite informally, but after he proposed this, they used it in quite a systematic way, and they were actually able to make some very concrete proofs about it. So let's go into a very, the foundational notation for congruency, which is if two numbers, let's say A and B, if I divide them by some fixed integer n, and they both give me some same remainder, upon dividing by n, I consider them to be congruent. And how I write this is that A is congruent to B mod n. There are, I think, a few different ways to write it, but this is the one that I prefer. It's essentially saying that A and B have the same remainder when you divide it by n. That's one interpretation of it. You can also manipulate it to be A minus B is congruent to 0 mod n, and open the bracket should be around the entire thing. If something is congruent to 0 mod n, that means we know that it's divisible because it has no remainder. So another interpretation of this is that n divides the difference of A and B. Is that okay? Right, nice. Okay, I'm going to ask you guys a question now. Let's say if we have a 12-hour clock and currently the time is 10 a.m. If 5 hours pass by, what is the time going to be? Hands? Joel. 3 o'clock, right? It's going to be 3 p.m. Joel, can you tell me how you did that?
Well, you just know that after 12, like after it goes to 12, then we'll go all the way back to 0 and then you can just, no, you can just count like from 12 a.m.
You can count, yeah, okay. Fair enough, you can count. If I did 10 plus 5 and I said that the time was 1500, would you agree with me? Petra?
Yeah, just take my 12.
Exactly. Joel has done subconsciously modular arithmetic in his head. We use modular arithmetic literally every single day without knowing about it. So when we did 10 plus 5, we did 15, and then we used mod 12. And then what is the remainder when 15 is divided by 12? Jaden? 3. So 15 is congruent to 3 mod 12. So in this 12-hour clock, if I give you any sort of number as time, then you can take mod 12 to find out what the corresponding time will be. Now let's get into something a little bit more concrete. We're going to something like the division algorithm. The division algorithm states if we have, let me drop this out. Let's say we have two integers a and n. I can represent a in terms of n as a equals q n plus r, where very strictly 0 is less than or equal to r is less than n. Can somebody try to make sense of this for me? How, what have I just written on the board? Joel?
So,
in words, try to explain what I've just said.
So I think that R would be the remainder.
Mm-hmm.
So essentially, if you had, okay, I don't know how to explain it.
Okay, that's fine, that's fine. So, you agree that as in, let's say, okay, for simplicity, let's say that n is less than a. I can multiply n by some amount of times so that qn, let's say I multiply qn times such that qn is less than a, but q plus 1, I'll write it as q plus 1 n is greater than a. That's what my q value is. It's going to be literally the, I guess, the limit, however much you can multiply n by, and then r is whatever is remaining. If r is 0, a is perfectly divisible by n. If r is anywhere which is not 0, it's not. Why can't r be equal to n? Somebody tell me. Lewis?
Because then r would be 0, which means
So if r is equal to n, the remainder is equal to n basically.
then it would just be the next multiple of
Exactly, the next multiple. If
q of n.
r equals n, then a is equal to q n plus n, and then a is equal to q plus 1 times n. But we stated that this does not follow the inequality. So that's the division algorithm. That is the, I guess you can say, the fundament of what we're trying to prove here. Let's say if we have two different numbers, a is equal to qn plus r, and then b is equal to pn plus k. Now if k is equal to r, we can very much say that when you divide a and b by n, they give the same remainder. So a be congruent to b mod n. Only if these two are the same though. If they're not, that means they're incongruent. Right? Is that okay with everyone? Nice. Now okay, let's actually get into some, I think we're gonna get into some axioms now. Actually no, before that, I'm gonna go through some examples. So let's say for example, 23 is equal to 4 times 5 plus 3. So can someone help me write this in congruence notation modulo 5? No one? That's fine, that's okay. I'll do this one actually for myself. I'll do, so 23, when I divide it by 5, I know that 5 goes to 4 whole times, but then there's a remainder of 3. So I can say it's congruent to 3 mod 5. Now, let's say, okay, I'm going to choose a different number now. I'm going to say 17. By using this method, by writing it like this, like the division algorithm way, and then using the congruence, can somebody tell me how to write 17 modulo 5? So,
You write it as is equal to 3 times 5 plus 3. No, 3 times 5 plus 2. And then you can say that 17 is congruent to 2 modulo 5.
2 modulo 5. Nice. Good. So tell me, Joel, would these two things be congruent to each other?
No.
Why not?
Because they didn't have the same remainder when you do it modulo 5.
Exactly. Yes, these two things are not going to be congruent to each other when you do modulo 5. Nice. So now we put like a slight graph of congruence, how we can determine if two numbers are congruent to each other. We'll go into some notation now. So let me rub this out. If A is congruent to B mod n, I said that there were two interpretations of this. I'm going to talk about one of them, which is dividing difference. This implies that n divides this symbol. People have seen this symbol before? If anybody hasn't, it just means it divides a minus b, which is just going to be the difference between those two integers. Okay, that is like that's like the very standard definition of that. There's nothing more really to it. Let's just do some we'll do some examples. Let's do some more examples, right? So somebody choose an n value for me. Path. Choose any random number.
3.
3. Okay, let's choose n equals 3. And then I want people to give me like a and b values such that they're both congruent to each other mod 3. Anybody want to have a go? No? I'll start off. Okay. I'll do 17 and 14. 17 is congruent to 2 mod 3. And 14 is also congruent to 2 mod 3. And thus 17 will be congruent to 14 mod 3. Can somebody give me any other examples? Joel?
Is this with 3 as well?
Sorry?
Is this also with 3?
What is? This with 3, yes.
Okay, so then you can have, 22 is congruent to 1 mod 3.
So what is 22 congruent to?
1 mod 3.
It's 1 mod 3. And then, okay, then 1 is congruent to 1 mod 3, okay. You can see sort of like a pattern emerging, not really, but kind of. With the division algorithm, if two numbers differ by an integer multiple of the fixed modulus, they are congruent to each other. I have just said maybe it's just a bunch of random words to you, but what I'm saying is actually very simple. If two numbers, A and B, like we had, actually no, I'll use two different numbers, let's say like X and Y. If they differ by by an integer multiple of the fixed modulus, if X minus Y is equal to nk, then they are congruent to each other modulo n, because x minus y will be an integer multiple of the fixed modulus. This will be congruent to 0 mod n, because what happens if I divide nk by n? What remainder do I get? 0. Nice. So therefore x and x minus y, the difference, is going to have no remainder modulo n. Okay, nice. So I think we've got an okay grasp of the basics. Does that make sense to everybody? Yeah? Nice. Any questions? No? Good. Let's go into some actual axioms now. Actually, wait, no. First, I'll go into why do we call it the theory of congruences. There are 4 things which defines a theory. 1 being the definitions, 2 fundamental properties, 3 derived theorems. The derived theorems for congruences are very, very interesting, and we'll go through them in the next session where we're going to learn about CRT, Chinese remainder theorem. And number 4 is applications. I showed a very simple application at the start, which was the clock, but yeah, that's why we call it a theory. But it's very much, it's very much like proven. But yeah, okay, let's go into some actual axioms now. So the first axiom is the equivalence, which is A is congruent to A mod n. This one is very trivial, because if we use the definition where it divides the difference, n is going to divide a minus a, so n divides 0. But any integer divides 0, hence n can just really take on any single value. So a is, that's a very trivial result. That's also known as the reflexive property. The symmetric property is that if a is, let me write this, this is the symmetric one, symmetric. If a is congruent to b mod n, then we have that b is congruent to a mod n. These seem very trivial, but they're also very important as well, I think. And in terms of differences, this one would produce a difference of a minus b, and then this one would produce a difference of b minus a. One of them, if they're not equal, one of them is going to be negative, but notice that a minus b is equal to minus b minus a. So if it divides that, it's going to have to divide that too. So we're still saying the same thing. I'll keep that there. The last one is the transitive property, which is that if a is transitive, if a is congruent to b mod n, and then b is congruent to c mod n, then that means that a is congruent to c modulo n. Does that make sense? Nice. Okay. So somebody give me an example of the transitive one. Come on, I want somebody else to do this one. Anyone? Daniel?
So like if in this case n is 5,
Let's say n is 5, yeah.
then a could be 1, b could be 6, and c could be 11.
Nice. Daniel's used the thing that I said before, which is that if integers differ by an integer number of multiples of the fixed modulus, and they're going to be congruent to each other. This time he just chose to add 5 and add 5, which is the most simplest example, but a very good example nonetheless. So we've talked a lot about 2 integers being congruent to each other. We say that they belong to the same congruent class. So how I denote that is, let's say if, I'll grab some of this out. If I'm working in, let's just say I'm working in modulo n. All of the numbers which belong to the congruent, I denote congruent class with square brackets 2. Any number which is belonging to the congruent class of 2 is going to be the set of all numbers which are p n plus 2. Given that n is greater than 2 as well. Let's say just n is greater than, well, strictly n has to be greater than or equal to 1, because modulus 0 doesn't actually mean anything. So n is going to have to be strictly greater than or equal to 1, but for the sake of, this one we'll say n is let's say n is 5, for example. All the congruent classes of 2 is going to be in the form Pn plus 2, for any p, we'll say, yeah. For any integer number multiple of p, all of the congruent class which belongs to 2 is going to be of the form Pn plus 2. Likewise, for some congruent class k, where k is less than n, this is giving the form of Pn plus k for any p. Does this make sense? Right? Okay, so congruent classes, they can go on forever. So let's say if I, with my example before, n equals 5, the congruent class of 2, I'm going to start off with 7. What is like, and the next one would be 12, the next one would be 17. Somebody keep going on. Is it able to keep going on?
22.
22. Just keep shouting out.
And then 32 and 37. Just keep it.
27, 32. Yeah, I'm just like, I keep adding on 5 every time because I'm just incrementing this by 1, right? That is the idea of a congruence class. So when you say like, you can say when two integers are congruent to each other, like every single integer in a congruent class are all congruent to each other. Nice, okay. Everything is making sense so far? Nice. Okay, now let's get into some like arithmetic of congruences. So, let's say if A is congruent to B mod n, and C is congruent to D mod n, then this might, like what I'm about to say might seem like a trivial result, but it's actually quite substantial. A plus C is congruent to B plus D modulus n. This is, I just added these two things, but I'm perfectly allowed to do that. The remainder when A plus C is divided by n is the same as the remainder when B plus D is divided by n, because these two remainders give the same thing, and these two remainders also give the same thing. Yeah? Nice. That is just the, addition axiom. Subtraction works the exact same way, so I can do plus minus. It's going to be the exact same thing. Petra?
Can you multiply them or not?
We can multiply them, that's actually the next one. So if we have the same thing, let's say we're like given this, and then we're given this. That means that AC would be congruent to BD modulus of n. We can very much multiply them, and also we can also divide them, but like as in that's a little bit more complicated because if C doesn't divide A, you get a fraction. Fractions do work, but that's going to be for I think a different time. The next one, which I think is very important, is powers. You can use powers of these quite a lot. If A is congruent to B mod n, A to the power of k is congruent to B to the power of k mod n. So we have addition, subtraction, we have the multiplicative one, and they also have a power one. Those are the three like axioms you can say of modular arithmetic. Now we get to a fun bit, which is reduction using modular arithmetic. So let me ask you guys, if I have number 99 squared and I divide it by 7, what is the remainder? How long, like estimate how long do you think it would take by using numerical methods? How long do you think it's going to take this?
Like 30 seconds.
With using numerical methods? Yeah, actually, yeah, 30 seconds, yeah, you just multiply them out and you find it, yeah, exactly. So around 30 seconds, like maybe a minute or something. The congruences take less than 10 seconds. Because we only consider, let's use the power that we did before, which was A to the k is congruent to B to the k, modulus of n. I know that 99 is congruent to 1 modulus 7. And when I divide it by 7, I know it's congruent to 1. If I square them, I still have the same property. They're still congruent to each other. I've not broken any laws. But now I have that 99 squared is congruent to 1 mod 7. So I've just answered my question. The remainder is going to be 1. And you can see how fast I've done that. So when you have, like, I don't know, 99 to the power of k mod 7, it will always be congruent to 1. Regardless of what k you use, it'll always be congruent to 1. And 99 to the power of, I don't know, like 7 million will be, when you divide it by 7, we'll have a remainder 1. So you can essentially like ignore the power, you can focus on the base only, and you can find its congruent modular number, which is within the range, and that's going to be your, we can also use it like I think in 2 steps. So let's say if I choose like, if I choose 80 to the power of 4, and I divide that by 7, I can use mod, and I want to find the remainder, I would first use that this 80 is congruent to what is it congruent to what mod 3? Mod 7, sorry. Then 3 mod 7. So I have that 80 to the power of 4 is congruent to 3 to the power of 4 mod 7. This is not entirely obvious to me, but I can just easily compute 3 to the 4. It's a lot easier than computing 80 to the power of 4, I'll tell you that much, but 3 to the power of 4 is going to be 81. 81 is congruent to 4 mod 7. So the entire thing we're doing right now with congruence is reducing it down to a number which we can very easily compute. And then from there we can find the remainder very easily. We can find out if things are divisible, we can find out the remainder if things aren't divisible. We're just reducing it down to a value that we actually like, a value within the range, within the fixed modulus. Okay, does that make sense? Nice. We can also use some equations, like some modular arithmetic equations. I'll start with a very simple one. Let's say that x plus 2 is congruent to 4 mod 7. So I'm asking you for a number which, when I add 2 and divide it by 7, gives a remainder of 4. Does anybody have a guess to try to solve this one? No? That's okay. I'm going to first take away 2 from both sides. X is going to be congruent to 2 mod 7. This is just like generally just a one-liner, and that means any number which is a part of the modulus class of 2 is going to be a solution to this equation here. So any number in modulus class of 2 will satisfy this condition, and this is going to be equal to, as we said before, p n plus 2, where in this case, I mean, n is equal to 7 for any, right? Nice, okay, let's go through another very simple example. Let's say 2x plus 5 is congruent to, let's say 11 mod 3. So anybody have a go at this one? Joel?
You're allowed to take away the 5 from both sides, you get 2x is congruent to 6 mod 3. And then I think you're allowed to divide both sides, and you get x.
100%. You're definitely allowed to divide by both sides, because you know, if you have, like we said before, that AC congruent to BD, right?
Yeah.
Now let's say that D is equal to C, that means that AC is congruent to BC mod N. We can, like, A is congruent to B, so we can divide both sides by C. This works like arithmetic, this works with all the arithmetic rules. You can divide both sides by the same integer, you can minus, you can add, you can do all those things as well. So this is going to be, what is it going to be?
That's x congruent to 3 mod 3, so x congruent, so well, you can say x congruent to 0 mod 3.
X is congruent to 0 mod 3, which means any number which is divisible by 3 satisfies this condition, right? Okay, nice. I might go through one more example of that. Yeah, okay. I'll go through one more example. I'll choose x plus 4 is congruent to 2 mod 7. It's much like the first one, except I've just switched around the numbers, but I'm going to reveal something like quite important. Go on.
You see, for the multiplication rule earlier, where it's like you have A is congruent to B mod n, and then C is congruent to D mod n. Do you like C and D strictly have to be integers, or can they also be like fractional?
C and D can be fractional, but I'm not doing that today.
Okay.
But they can be fractional, yeah. Yeah.
For the power rule,
A to the
K
A.
to the K is a half.
K is a half.
K and
Roots.
square numbers, yeah.
I think with square roots, it tends to, I don't think a K has to be an integer in that case, because like when we go into quadratic residues, 2 numbers can have the same quadratic residue, except you won't really find out the next one. As in, let's say if I have let's say we're working in modulo 4, any number is going to be congruent to 0, 1, 2, or 3 modulo 4, right? You agree with that, yes? Yeah, also this is another way of you can say any number, when you divide it by 4, has to give a remainder of 0, 1, 2, or 3, right? So any number is either in one of these modulo classes, modulo 4. So if I square this, k squared, it's going to be congruent to 0, 1, 4, 9 mod 4. Now let's reduce these down. K squared is going to be congruent to, this is 0, this is 1, that's fine. This is going to be 4, this is 0, this is going to be 9, which is 1. So it's going to be just 0 and 1 mod 4, right? Now let's say if I just gave you that k squared is congruent to 1 mod 4, right? If I square rooted both sides, yeah, sure, I'll get k is congruent to 1 mod 4, but you're missing out the solution where k is congruent to 3 mod 4. That would not be very, I mean, like, yeah, it wouldn't be very obvious to you at the start. Maybe this example is like pretty nice, but it wouldn't be very obvious to you. So I think let's just keep k as an integer right now. But yeah, let's go back to the, it was a very good question. Let's go back to the original equation. I'm gonna actually, yeah, okay, this is fine. Does everyone want to try to solve this one? Daniel?
So 2 mod 7 is congruent to 9 mod 7. And at that point you can take 4 away from both sides. So x equals 5 mod 7.
And then x equals 5 mod 7, yes?
Yeah.
Nice, yes, exactly. If I just take away 2 from both sides, I would have said that x is congruent to minus 2 mod 7. Are me and Daniel getting different answers? Somebody tell me. You shake your head, why not?
Because you can just add 7 to each of them they're all separated by a difference of 7. So
Exactly, so in more formal language, they belong to the same. They belong to the same congruence class. So I'm actually, these are the same thing. Okay, let me go through, I'm gonna actually go through one more example because I wanna use the trick that Daniel has used because it's actually very good. So let's say that 2x plus 3 is congruent to 4 mod 7. Oh, can somebody try to solve this one? Victor, you wanna try? No? Okay, that's fine. I'll go through this one. I'll use like the same thing that Daniel used. I'll take away 3 from both sides. 2x is congruent to 1 mod 4. Sorry, mod 7. The problem is I can't divide by 2 now because x is congruent to half mod 7. Like x is an integer. I'm trying to look for integer solutions. So what I can do is, I'll do what Daniel did. I can either add 7 or minus 7. I'm going to add 7 in this case. I'll get 2x is congruent to 8 mod 7. And thus x is congruent to 4 mod 7. This is my answer. Does that make sense? John?
I'm a bit confused by it. Is like, so the multiplication thing applies differently with fractional things, because if I said that, okay, if I considered like a half is congruent to a half mod 7 by that rule that we established earlier, the one that was kind of intuitive, and you have a half is congruent to a half mod 7, and then you have like 2 congruencies, and then surely you can multiply them together to get x is congruent to a half mod 7 as well, which, like, intuitively it makes no sense. Like, it shouldn't be able to be congruent to a half. I don't see why that doesn't work under the rules that we've already
Because
established now.
if x is congruent to a half mod 7, does that give me integer solutions of x?
No, yeah, it doesn't give you integer
It doesn't give me
solutions.
integer solutions. You'll actually find out that a half is actually congruent to, half is congruent to 4 mod 7. That is actually true.
Oh, okay, so.
But
okay,
that's
so
what I'm saying, that the fractions get a little bit technical, but I mean, we're going to go through that in the next session.
Okay, which makes
But-
sense.
Yeah, it does link back. I see where your confusion is, but I think this method is a lot simpler. If you can't divide, if it gives you a fraction, just keep upping it, keep downing it,
Okay,
and
that
get
makes
something nice. Okay, the last thing we're going to go through is multiplicative inverses. So this one is actually some like proper like genuine terminology. So multiplicative inverses. If I have 2 numbers a and b, which belong to the set of positive integers, right? And they both satisfy the congruence that they satisfy. A, b is congruent to 1 mod n. Then b is the modular inverse of a, or just maybe the inverse. You don't have to say modular inverse, but let's just say inverse of a modulo n. Likewise, by symmetry, a is the inverse of b modulo n, and we can use the same thing that I derived, like I've not derived, but the same thing that I did before, which was if I have, let's say, 3x is congruent to 1 mod 7, right? Then how can I try to find the, actually wait, should I say mod 7? I'll say, okay, let's say mod 8 actually. Let's say mod 8, let's make it a little bit simpler. X is going to be my modular inverse. So how can I find the modular inverse of 3 mod 8? Any ideas?
Is that what we did before?
Yeah, the thing that I
So
did
you
before.
want to find a number that's 1 mod 8 and also
What can I do to
0
like,
mod
just solve this equation?
3. If you add 8,
If I add 8, yep.
it becomes 3x is congruent to 9 mod 8.
Mm-hmm.
So then x is 3 mod 8.
Exactly. So any number which is congruent to 3 mod 8 is going to be the inverse of 3 modulo 8. Does that make sense?
Yeah.
Nice. Okay. Let's do. Let's try to do one more example. Let's do 4x is congruent to 1. I'll say mod 5. So I want somebody to give me the general form and also just some possible numbers as well. Does anybody want to try? Actually, I'll do this one. So I can go two ways for this. If I try to bump it up by 1, then that's going to be 4x is congruent to 6. If I try to do it again, it's going to give me 11, and then I do it again. There's going to be I'll keep going until I get to 16, something which is a multiple of this. Or I can go backwards. Going backwards is not a bad thing at all. I'll be going backwards. I'm getting that 4x is congruent to negative 4 mod 5, and x, I can divide x by 4, and then I can divide both sides by 4 to get x is congruent to minus 1 mod 5, and thus x is going to be congruent to 4 mod 5. And then for some examples, I can say that x is equal to 9. Any number which is in the modular class of 4 mod 5 would be like sufficient for this. X is equal to 9. 4 times 9 is 36. 36 is congruent to 1 mod 5. Yeah? Nice. Okay. I think that would basically cover what we're, yeah?
Yeah, so when you like found the modular inverse and the multiplicative inverse, what is useful about finding the multiplicative inverse?
What is useful about it?
Yeah.
Is the thing that you said before, the fractionals. So, you know when I said that, okay, let's try a new example. So, 3x is congruent to 1 mod 7, right? If I add 7 twice, 3x is congruent to 15 mod 7, x congruent to 5 mod 7, mod 7. I choose x equal to 5. Then, modular inverse, quite literally, 3 to the power of negative 1 is congruent to 5 mod 7. It's the exact thing that you said, fractionals. 1 over 3 is congruent to 5 mod 7. Right? Because, like, if I divide both sides by 3, x is congruent to a third mod 7, right? But x is congruent to 5 mod 7. So 5 is congruent to a third mod 7. That's where we can introduce our fractions. And we'll look a lot more into this into probably the next lecture I do on this. But that is the idea of modular inverses. So that will basically cover anything I'll be teaching. For your guys' own interest, if you guys want to look more into this, I would suggest looking into some theorems. There are some books as well that you can look at modular arithmetic. I suggest Modern Olympiad Number Theory. There's also the book that I followed, which was Elementary Number Theory by David M. Burton. That was a very good book. I really enjoyed that a lot. It's a little bit simpler than Mont, but I think it builds a foundation up quite well. And it teaches a lot of this stuff like quite thoroughly. I think it has like 2 or 3 chapters, 2, 3, 4 chapters on just modular arithmetic. It's really good. Some interesting theorems. We can do the Fermat's theorem, not to be confused with Fermat's last theorem, but rather Fermat's little theorem, which is a to the power of p minus 1 is congruent to 1 mod p for some prime p, for some prime p. There's also Wilson's theorem, which states that p minus 1 factorial is congruent to 1 mod p. And then there's also one which uses the Euler-Tauschig function pretty well. And that one is, in case you can just call it Euler's theorem, which is if phi n denotes Euler-Tauschig function, then a to the power of phi of n is congruent to 1 mod n, where a and n are both co-prime. These I'm not going to go through in the next session or the session after that. These are like quite very, very in-depth. You can do quite a lot with this. The idea of reduction, it reduces things down quite like a lot, but some interesting theorems to look at nonetheless. Thank you guys.